Okay, welcome back, everybody. I wanted to say like a couple more things about team ranking problems that we've been doing. Basically, finish that stuff up. So, uh, the just to remind you, uh, this what we were calling the Massey method. If all of the teams played each other as indicated, would basically amount to the point differences between all of the teams. So if you like, you can think of it as like predicting the point point values between all those games played if they were actually played. That's what the ranking does. So here, first, we write down the system of equations corresponding to the games played and the points won or lost. So write down. So write down system of equations corresponding to games played and points one. I'm just going to say points one because we saw that you can encode losses here as winning by negative points. So that's fine here. Where the rankings are the unknowns. So where the rankings are the unknowns. Right. So the rankings are the things that we are seeking to find here. So two, we're going to convert the system of equations to the matrix equation that we're going to solve. So convert the system to the matrix equation AR equals P. Right, as we did in all of those examples. Now, of course, this is typically not going to have a solution, so we are seeking solution here to the least squares problem. So we're writing out the normal equations for this matrix equation. So write out the normal equations, which is A transpose A times R hat is equal to A transpose P. Then, of course, the issues that we encountered here, right, is that we really want to ensure that we don't get infinitely many solutions here, because in our context that would mean that there's not like there would be infinitely many rankings we could choose, and that's not typically a thing we would like to have when we think about coming up with a good ranking for teams in some sport. So we want to alter these normal equations in such a way that what we get as a result has a unique solution. So the way that we alter this is we change. This is where the Massey method comes in here, because up until this is just least squares, right? This is what we've been doing the whole time. So here I want to change the lower row of the new matrix on the left. So change the lower row of the new matrix on the left to all ones. And the last entry of the new vector on the right to 0. And for reasons that I explained in the last lecture, this will guarantee that the thing has a unique solution, right? The easiest way to see this is that we had this fact about this matrix here. We called this matrix M at this point. So in the last lecture, we called this matrix M. And then we also called it M once we did the change. But basically, this M had special special properties, right? We called this M, we called this Q. So at the end of the of yesterday's uh, or well Friday's video, we had this listed as MR is equal to Q. Okay. And so we called it this even after we did this change, but before we did the change, the thing we noticed about M was some properties that its rows had. So namely, that the rows were definitely linearly dependent, but if you removed one of them, then the remaining rows were linearly independent. So we got this fact that if we removed one of the rows and say replaced it with all ones, then what we get are linearly independent rows, and then the last row is perpendicular or orthogonal to all of them. Its dot product with all those other rows is 0, so the resulting rows that you get are linearly independent, so that you're guaranteed to get a unique solution. That was probably the quickest way of seeing that this is always guaranteed at this point. And then now we solve this MR equals Q. Okay, that solution is our ranking, right? This gives us our ranking. Now this is exactly how the process goes. Now what is maybe, the more annoying part of this? So like all of this is pretty mechanical once you get to this point, writing out the normal equations, going from there. So then really this first bit of like encoding the games won and lost is kind of, you might say one of the more annoying parts, especially if you have, because think about how this would be, right? So for instance, in your homework, you were asked to do this for a league where there are 8 teams, and those 8 teams, I don't think I made any of them play each other twice. I can't remember. I don't think any of them played each other twice. Maybe I'm wrong about that, but I think all of them just played each other once. But if each of them had like a home and away series of games, then it would have been even more, right? It would have been like roughly double the amount of games played. And if you actually write it out by hand, all of the, or even not by hand, if you just write out the system of equations like that, it is kind of annoying. There's a lot of them. So the question is there a way that we can shortcut some of that work and not have to do so much work in writing down these system of equations, which, again, this is, this is very straightforward, but is there any way we can save time on the work here? And the answer is yes. In fact, we can. There is a slight shortcut that we can do here. So I will introduce that here. So shortcut. So what is this shortcut? Notice from previous facts about the matrix M, right? We can actually directly fill in the matrix M. The right-hand side vector, right, is we'll talk about that in a second of how we get that. But we can directly fill in M. So how can we do this, right? So question: how can we go directly to MR equals Q? Well, we know that we're putting the last row as all ones, okay, but that just helps us with one row. Okay, but we know that the other entries come from, the other entries, as we saw last time mathematically why this is the case, but the other entries in this matrix have to do with the number of games that the corresponding teams, the teams corresponding to those indices, played against each other, right? So we knew what the diagonal entries were, right? This is the total number of games played by the given team, and then the off-diagonal entries were the negatives of the number of games played by the corresponding teams, right? So first of all, so last row is all ones. Okay, so we got that taken care of. Okay, in the other rows, how do I figure out what m sub I and m sub ij is? So m sub I is the number of games team I plays. And m sub ij is minus the number of games, and this is for I not equal to j, because this obviously doesn't work if I and j are equal. So m sub ij is equal to the negative the number of games teams I and j played. Against each other, right? Maybe I'll add that as a parenthetical statement within the parentheses. Okay. So this means that we can actually fill in all of m just by tracking this from the list. Rather than writing out system of equations, go through all this process, writing out A atoms, A transpose, blah, 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 we can actually just directly fill in the matrix M. So that's the thing. That's the key here, right? Now, what about Q? Right. So we got this taken care of. What about Q? Well, for Q, we know that the last entry is 0. But what about the rest? Well, remember, this was also one of our facts about that equation. Other than that entry, for each other entry, we'll say Q sub I. Q sub I is the total number of points team I earned. Okay. Now, what we mean by that is, if you're thinking about this, it's rather than being, necessarily the absolute like number of points they earned, it's their total point differential, right? That's what is actually being computed here, because we might, all of this info you're giving, you're not actually given info about like how many points a team won, right? We're thinking about it in terms of how many points they won by. What is the difference between the point total? So that's what is meant here, right? So in our context, we're calling that the points that they earned, but just keep in mind that if you're doing this for a game and you're just tracking the point differences, that's what is meant here. It's the point differences. And so the point is that we can, no pun intended, the point is that we can actually track all of this without resulting, or without resorting to writing out, going back here, writing this out and going through this whole process of least squares. Knowing what we know about m, we can actually fill it in directly. Now, if you would prefer to go through this process, you absolutely can, but this is just showing you that you don't have to. You can actually arrive at the same amount of info filling it in like this. There's an example, 5.1, that I won't do, that you can do, that is kind of like a shorter version. So check this for example 5.1 in the notes. So example 5.1 in the notes. If you check to see how the shortcut is used, you can see how it can be used. And then the homework, the corresponding homework problem that is similar to this, instead of having 5 teams, you have 8 teams. So it's just a slightly bigger matrix that you get, and you can apply that exact same thing. Okay, so then how, just tidying up kind of the remaining questions you might have about like how this team ranking goes. So question, what does the ranking mean again, right? So the first thing, first, rankings are relative. Okay. The rankings are relative to one another. So if you say that some team has a ranking of like 2, right, for a given league, season, whatever it is you've tracked, that you're not able to take that info and say anything about another league, that is computed separately. You could say something about where that team lies in the season in question, but taking that data and trying to say something about another season or another league where different matches are played, different games are played. That's not really something you can do. It doesn't have any kind of absolute meaning until you compare it with a ranking from the same computation, right? But the idea is that the rankings should maybe determine is the wrong way to say it, should predict outcomes in the following way, right? Like what is R sub I minus R sub j as the rankings? This ought to equal, this ought to be the number of points Team I wins by in a game against Team J. Now remember, this losses are tracked here by negative. Losses are tracked here using negative numbers here, so winning by -5 is the same thing as losing by 5 points. Okay. And so, this we can handle all outcomes here. But this is the idea, right? This is the original way that we defined these rankings, and so this was this is, maybe I should say that we're baking this in, right? It's not a question of whether this happens. This is literally how we define these rankings. But it's nice to remember that this is the purpose, and this is what it's supposed to be doing. Okay. So a quick example, right? Say we have ranking as follows. This is actually the answer to example 5.1 that I told you to check. So in this example, if you track through the example 5.1 that I'm talking about, teams 1 and 5 don't play each other. So team Team 1 and Team 5 don't play each other. But Team 1 has ranking minus 0.002899, and Team 5 has ranking 1.012. So even though that they don't play each other, right? If they did play, then the outcome would be r sub I, or we'll say r sub 1 minus r sub 5, which is, for these two, is minus 0.002899 minus 1.012, which would give me minus 1.104099. So this is what we get. Which means what? That Team 5 would win by that many points, i.e. Team 5 would win or should win by 1.104099 points. So this is what we mean when we say using these rankings to predict games or matches where teams didn't play, right, in the same computation. So in your homework example, there's at least two teams that don't play each other. So you can do the same thing. I didn't ask that question as part of the homework problem, but you can yourself consider, based on those rankings, what should happen if those teams did play, right? So computations like this, not necessarily using Massey's method, but using various other methods to rank teams and to come up with some sorting of the teams that makes sense in the same style, in the same fashion, as how you get betting lines for teams, or how these things are computed so that you can say, oh, this team is a 5-point favorite, or this team is a 10-point underdog, right? If you've ever wondered where those computations come from, the answer is things like this. So like I said, not necessarily using the same method, but this is kind of in the same family of methods. So notice a few other things. As mentioned before, we already take into account ties. We account for ties as this or this, doesn't matter, right? Winning by 0 points is being a draw or a tie. Okay. So ties are taken into account. What if teams play each other more than once? Well, we already took care of that, I think, in the very first example that we did last time. So what about multiple games? So what do I do here? Well, in the context of Massey's method, I simply have two identical equations on the same line, right? I simply have two identical equations for the same line, i.e., you know, I would have something like, you know, r sub I minus r sub j is equal to 1, and r sub I minus r sub j is equal to minus 2. So what would that indicate? The first one is team I and team J played, and team I wins by 1. And this one is team I and team J play, and J wins by 2. Okay, or leaving it as I wins by minus 2, right? But this is, they played each other twice, right? So they played each other 2 separate times. The first time, team I won by 1 point, and the second time, team J won by 2 points. So this is how this would go into your equation. Of course, you could also keep track of this in the shortcut, right? So I'm not saying that you have to still stick to writing out the systems of equations like this. You could actually still use this in the same way in the shortcut. Okay. So here's another way that we can alter things. So what if we want to weight games differently? So for the purposes of the ranking, maybe we want to give certain games more importance, right, in the computations, more prominence in the computations than others. There's a variety of reasons you might do this, right? There's a variety of reasons you might want to make one game factor in more heavily than another, right? From it actually being a structure of the game themselves, where some games are worth more, or to, you know, if you're trying to assess, you know, relative strengths of the teams, you know, maybe one team suffered a lot of injuries when they played in a particular game, and you want to kind of you know, skew your computations against including that and on equal weight with the others. So that's you know, that's another reason that you could do something like this. But how would you do that, right? How would you actually weight the games differently? Well, so a couple things we could do. First, we could increase the point difference. Maybe I'll put this first. We could increase the point difference. So, like, for instance, so i.e. a win by 3 points could be considered as a win by more than 3 points. So that's one way that this could be done. Okay. Another way we could count individual games more than once, right? We could record the game or the match more than once. Okay. Now there's pros and cons for doing it either of these ways, right? You might say, well, recording a game some number of times, that's a little less granular because it's like you either make it count twice as much, 3 times as much, 4 times as much, or so on, versus increasing the point totals. Allows you to you could toy around with those numbers, which maybe you view that as kind of arbitrary. So anyway, that's there are reasons why you might do that in a particular setting. But what is kind of the limit here? If we had disconnected sets of games, this might be a problem. So, for instance, imagine a league made up of two sub-leagues where the teams in question play each other within each league, but there's no cross-league play, right? If you tried to make a ranking with those, Massey's method wouldn't work, okay? At least not as we have it, okay? Because the resulting matrix we get would be this block matrix, and replacing the last row with all ones wouldn't work here, because the last row would not be a shared last row for both of those things. It would be a last row for one of the block matrices, but not the other. So we can't exactly do that because we would still have linear dependence, because basically we're not replacing both last rows, and we can't do that. So that's an issue. But what should I say here? Well, there are things that we could do so that we could essentially split this up, applying the Massey method to each sub-league, and then maybe trying to say something. But this is something I will let you consider, and I might include this in a future thing. This might be maybe a question that comes up on a midterm or something. But that's just something for you to think about as far as limitations of this thing. That's more or less all I wanted to say about team ranking stuff. I've already spent enough time on it, even though this is a nice, fun application of some of this stuff. So I wanted to end here with a discussion of this. So moving on from team ranking and giving ourselves a little bit of a break from least square stuff, since we've been doing that a lot, I want to cover what is called the Leontief Input-Output Model. Okay. So what is this? Leontief himself was an economist. Essentially introduced this model for economies that we're about to discuss. This is actually an early example of. It's not. It's not. The first. There were some like analog computer results used. I think the first thing that computation in that sense was used for was computing Bernoulli numbers. This is all the way back in the 1800s. So technically, I believe Bernoulli numbers were the subject of the first algorithm in that sense. Of course, the oldest algorithm itself is probably the Euclidean division algorithm, which is stated in Euclid's Elements. So about 2,300 years old. Algorithm itself comes from the anglicization of a Persian mathematician's name, Al-Khwarizmi, that became algorithm, and it so named because there were algorithms described in his book. Actually, is Al-Khwarizmi? I believe he's also the one who wrote the book with a really, really long title, but one of the words in the title is Al-Jabr, which is like which is the thing that algebra is named after. So anyway, this is from a similar place. Even the word algorithm comes here. It's not the first the first use of computer to compute thing, I believe, is to compute the Bernoulli numbers. This is from the 1800s. This is one of the earliest uses of the computer to do this sort of computation. Was 1949, I think. Anyway, this guy won Nobel Prize in '73 based on this work. What is the approach here? The approach is we're modeling an economy. Economy is divided into sectors. Okay. And each sector produces a product. Now, the idea is that in order to produce a product, right, which we might think of as producing some number of units of a product. So you could normalize and say, okay, how much does the sector require to produce 1 unit of its product? In order to produce the product, it may need input from all the other sectors. It might also need input from itself. Okay, so in order to produce product, in order for each sector to produce product, it requires input from possibly all other sectors, possibly including itself. Okay. Now, maybe not. Maybe it doesn't require input of its own product to produce its product, but maybe it does. Okay. So, this is the idea. So then, what is the idea here? There's the demand that each sector has or generates for producing its product for the other sectors. This would be called the internal demand. And then there's also demand that may come externally from outside of any of those sectors, right? And so the way to write this is that the total amount produced is the internal demand plus external demand. Okay. All right. How do I want to come up with an example that illustrates what it is that's going on here? Well, let's say that we have an economy with 3 sectors. Each producing units of its product. Okay, in order for each sector to function, it needs some of its own product as well as other sectors' products. Suppose we have the following. Okay, so maybe I'll say the first thing. For sector 1, to produce 1 unit of product 1, it takes 0.1 units of product 1 0.2 units of product 2, and 0.25 units of product 3. And I'm going to write product 3 as P3 from here on. Same thing with the rest of the products. Okay. All right, so that's for sector 1. Next, for sector 2, to produce 1 unit of product 2, or sorry, I'll write it as P2. It takes 0.15 units of product 1, 0 units of product 2, so it doesn't require any of its own production in order to make product 2, and 0.4 units of product 3. And lastly, for sector 3, to produce 1 unit of product 3, it takes 0.12 units of product 1, 0.3 units of product 2, and 0.2 units of product 3. Okay, so just putting on your screen again what those 3 things are. There it is. Now, what is the goal here, right? The goal is for sectors to produce, for sectors altogether to produce P1 units of product 1, P2 units of product 2, and P3 units of product 3. Don't confuse these piece of 1s, piece of 2, and piece of 3 with the P1, P2, and P3 that I did here to abbreviate product 1, 2, and 3 here. Okay, so these are unknown P's. Then the question, so if the goal is for sectors to produce this, okay, then what is the total internal requirement? Okay. So I'm going to translate these things that I've written here into what this would mean for internal requirements. So for instance, consider for product 1, right? So for product 1, what is required? So let's just track this. To produce P1 units of product 1, I need, So I require how many units of product 1? Well, let's see. So P1 units of product 1 requires, for sector 1 to produce 1 unit of product 1, it takes 0.1 units of product 1. So to produce P1 units of product 1 takes 0.10 times P1 units of product 1. Okay. What about to produce P2 units of product 2? To produce P2 units of product 2, how much product 1 do I need? I'm going back to this statement. For sector 2 to produce 1 unit of product 2, it takes 0.15 units of product 1. So I require 0.15 times P2 units of product 1. Now, why are we multiplying by P1 and P2 here? Well, because these original statements here for all of these were the requirements to produce 1 unit, right? So if we're producing P1, P2 units, this is, I'm scaling it by that amount, all right? That's why it's important to know this for production of a single unit, right? Of 1 unit. And then lastly, to produce P sub 3 units of product 3, I require 0.12 times P sub 3 units of product 1. This is directly from the page here. Okay. So this is telling me for each amount of the products that I want to make, how much I need of product 1. Okay, and so in total, the total amount that I need of product 1 to produce these products that I want to make, this number of products I want to make, it's the sum of these things. Okay. And so, similarly to this, I can do this exact same thing for product 2 and for product 3. And so, putting all that together, what do I get? I get that we need 0.10 P1 plus 0.15 P1 plus 0.12 P sub 1 units of product 1. We need 0.20 P sub 1 plus 0 P sub 1. These are not P sub 1. This is P sub 2 and this is P sub 3. Sorry about that. That's going back here. I simply copied this wrong, right? P sub 1, P sub 2, P sub 3 here. Okay. For product 2, we need 0.20 P sub 1 plus 0 times P sub 2, because it did not require any of its own product in order to make this thing, plus 0.30 P sub 3 units of product 2. And lastly, we need 0.25 p sub 1 plus 0.40 p sub 2 plus 0.20 p sub 3 units of product 3. But then, of course, all of this need is to produce the goal, which is, remember, the goal is to produce, for all the sectors, to produce piece of 1 units of product 1, piece of 2 units of product 2, and piece of 3 units of product 3. And so, really, what I have here is the following system of equations. P sub 1 is 0.10 p sub 1 plus 0.15 p sub 2 plus 0.12 p sub 3, and p sub 2 is equal to 0.20 p sub 1 plus 0 p sub 2 plus 0.30 p sub 3, and p sub 3 is 0.25 p sub 1 plus 0.40 p sub 2 plus 0.20 p sub 3. So this is my system of equations that I get. Of course, I could write this as a vector equation, if you like, right? So we could write this as the vector equation, where my left-hand side vector contains the amount that I want to be producing, and then I have weights as these amounts, p sub 1, p sub 2, and p sub 3. Writing it out this way instead of going directly to the matrix equation has a purpose. So my purpose here is to indicate the role that these column vectors are playing. And we'll have a name for all of these things. So there it is as a vector equation. As I said, there's a reason I took my time to write it out like this. Of course, I can write this in matrix form just as well, maybe most conveniently, as my vector piece 1, piece 2, piece 3 is equal to my matrix. Just writing this again. Times my vector. And now we have one more thing that I want to consider in this process. I want to consider the potential for there to be demand that arises from elsewhere. Currently, this demand indicated here is the internal demand. That is, it's the demand that is indicated by my own sectors to produce these things. Okay? But I want to include the following additional external demand of D1, D2, and D3 number of units for the corresponding products 1, 2, and 3. Okay, and that means that in this way, so maybe I'll break this off here and say, if in addition we have external demand of D1, D2, and D3 units of the products, respectively, then the total that needs to be produced is this equation, as I have written here. This is the total produced. This is the internal demand. And this is the external demand. Okay. This allows us to see the general form that this model takes. So, what is the general form for this model? Bunch of definitions labeling these things. The Leontief Input-Output Model is given by P is equal to M times P plus D. Just check that this is in fact what we had written previously here. Yeah, right, that's it. Okay. Now, based on that previous example, we have some terminology. It's not going to be too surprising for you. So, M is called the consumption matrix. Its columns are called consumption vectors. So, column J of M is the jth consumption vector, and it contains what? So the reason that I wrote this out in the following way, when we had this expression and I wrote it out as a vector equation so that we can see the columns of this matrix, the columns of the matrix tell me what? So the first column tells me the amounts of, so what does this tell me? It tells me the amounts from each of the sectors for sector J to produce 1 unit of output, right? So in this case, 1, right? So what does column 1 tell me? It tells me exactly the output required for sector 1 to produce 1 unit of output. Okay. Similarly, this tells me the amounts needed, right, of each of these things for sector 2 to produce 1 unit of outcome. The reason you can tell that this is what it's saying is because the weight in this case is the amount that we need to produce, right? Here, same thing. This vector tells me the necessary input that I need from each of the sectors for sector 3, in this case, to produce 1 unit of output. Okay, so it contains the necessary input from the sectors for sector J to produce 1 unit of output. That's what the consumption vectors tell you. Okay. So, notice these are the columns and not the rows. Okay, which again, go back to this equation that I looked at, and it's clear what it is that's going on here. That's why I spent the time to write out this vector equation here to show you what it is that's going on, right? Because writing out the vector equation, you can just see that, oh, these weights here, multiplying the vectors, these vectors have all of the data you need to tell you how much you require to produce 1 unit of whatever that product is, right? And then here's the amount. Okay. The vector P is called the production vector. D is called the external demand vector. MP is the internal demand vector. Well, we know that, right? Let's go back to our, where did I put it? Here it is. Right. This is the internal demand. Up here, it's all of this. Because in the absence of external demand, right, this is just telling you like all you need in order to produce what it is you want to produce, right? Your goal production is telling you everything you need because it's telling you everything that these sectors need from themselves, right, from each other in order to make this happen. Okay, so then external demand is the thing that comes from elsewhere. The demand is coming now from outside of those sectors. Okay. One more line of things I want to talk about. So an economy is called open if the external demand vector is not the zero vector, and closed if the external demand is in fact equal to the zero vector. So a closed economy is one that has zero external demand, literally zero. There's no external demand whatsoever, so the only demand is internal. And an open economy is one where there is some, right, external demand. Now, closed economies are pretty rare, so while it's nice to have this as an example, this is, in terms of examples we're going to be talking about, usually we're going to be dealing with open economies because a truly closed economy is a rare thing, can almost be considered pathological. So we are going to be dealing mostly with open economies in this sense. Okay. All right. We will discuss this this example of a closed economy later when it comes up, but for now we're basically going to leave that off. We're going to mostly consider open economies. But how might we solve this? Because you might look at this equation I've written down here, and I'm going to rewrite it again. Okay, how might we solve this? You notice that, of course, P is on both sides here, so you have a very strong desire to do something. Maybe I should write this on my next, write this on the next page here. So we have P is MP plus D. If I was going to solve this, I want to put it in the form of every other matrix equation, right? I want to put it as an AX equals B type thing, which I can in fact do. I can move MP to the other side here so that this is P minus MP is equal to D. That's perfectly valid. Now, of course, remember how we did with eigenvalue and the characteristic polynomial and all of that stuff, eigenvalue, eigenvector definition. I explained on the first day of lecture how obviously if these were not vectors and this was not a matrix, you would think a little bit differently about how to do this. You'd say, well, I can factor out a p, right? So you'd be very tempted to do something like this, where you put 1 minus m times p here. But we can't really have 1 minus m times p. That doesn't make any sense because that would be a scalar minus a matrix. But what you're actually wanting to do is 100% fine, so long as you notice that this is what it is that's going on. Right? So while I cannot put 1 there, I can put the object that is 1 for matrix multiplication, which is the identity matrix, right? So this is I minus m times p is equal to d. Okay. So where this is the n by n identity matrix, m is going to be a square matrix for these things as well. So so this is what I have. Now, I have now put my equation in the ax equals b form. And so there's a number of cases, right? Whenever you have an ax equals b equation, obviously you know that there are a few cases to consider. So the cases, you could just say, well, I know that this either has 0, 1, or infinitely many solutions, which is true, but I want to say a little bit more specifically about this. So 1, if I minus m is invertible, then this has a unique solution, which we can write out immediately. That solution is I minus m inverse times d. Now, maybe you've lost sight of what it is we're even doing here. So going back to my original equation that I have written here, you might say, wait, what am I even solving for in this? And the answer is you're solving for P. So you are typically given the consumption matrix M, you're given the external demand, and you're solving for P. You're solving for the total production. And then, we will talk about like what some of these numbers mean for specific examples. So we're solving for this P. P is the unknown thing we're solving for, typically given M and D. All right, in case you were confused by what it is we're doing. So in this first case, if I minus M is invertible, it has a unique solution. There it is in that case. Okay, now you might say, well, what if I'm in the case of a closed economy? Not only is it in this same case where I minus M is invertible, it still has a unique solution, but its unique solution is just the zero vector, right? If I minus M is invertible and D is the zero vector, then our solution is also the zero vector. So it still has a unique solution. That's what we get from invertibility. But here, in this case, the unique solution is the trivial solution, which is the zero vector. Okay. All right. You can think for yourself for a second what that means, having a closed economy and this I minus M being invertible, right, where M is your consumption matrix, means the total amount produced is 0. Right. Think to yourself whether you think that makes sense intuitively based on what all these things mean. If I minus M is not invertible, then this may have none or infinitely many solutions. Now, if I minus m is not invertible, and the economy is closed, then there are infinitely many solutions. How to see that from 3? 3 is not saying much at all. Like this is kind of what you always know for a matrix equation ax equals b, where a is not invertible. Either has 0 or infinitely many. Okay. If d is 0, this is a homogeneous equation, and a homogeneous equation always has to have at least one solution, the trivial solution. So since it can't be in the unique solution case, that one solution can't be the only solution, so there has to be infinitely many. That's the reasoning here. Okay. Now, I'm going to pick up, I think I'll wait here and pick up tomorrow right here because rather than start on an example that I'm not going to be able to finish by the end of the lecture today, I think I will simply stop here and we'll pick up exactly here in tomorrow's lecture. So if you haven't had a look at the homework yet, do that. Let me know if you have any questions about it. It's due this Wednesday by 11:59. So let me know. Let me know. Like I said, if you have any questions, I'm going to hold some office hours maybe on Wednesday afternoon. I'll let you know. I'll send a link after Wednesday's lecture. Hang around a bit. It's homework. I might, depending on the nature of the question, I might not be like perfectly helpful. If I think it will be better suited for you to think about it more closely or more carefully on your own. But nevertheless, I'll try to be some level of helpful for some of those questions. But anyway, that's it for now. We'll finish this stuff tomorrow and then move on to the next topic. So I will see you all then.